Right. The space world is certainly buzzing about the most powerful explosion in the universe. A supernova has burst onto the scene in a galaxy quite literally far, far away. Astrophysicist Neil deGrasse Tyson recently made a groundbreaking announcement about our celestial neighbor Polaris. This shocking and unsettling update reveals that the once stable North Star, widely known for guiding navigators and serving as a steadfast point in the night sky, has undergone a shocking transformation. According to Tyson, recent observations indicate that Polaris has just exploded. The more I look at the universe, the less convinced I am that there is something benevolent going on, sending ripples of incredible cosmic events through our solar system and space at large. In this video, we'll discover the terrifying effects of this startling news that has left the scientific community and stargazers worldwide on edge. How did this fascinating star explode? What effect does this explosion have on Earth? Let's get into it. Astronomers and space enthusiasts worldwide are in shock following Neil deGrasse Tyson's unraveling of the mysteries surrounding Polaris's explosion. In a recent announcement, Neil highlights the urgent need for further exploration and observation of this fantastic North Pole star. He also emphasizes the potential consequences of Polaris's explosion, hinting at events that could reshape our understanding of the cosmos. But that's not all, because even after the explosion of this celestial body, something terrifying is said to have emerged. But what is Polaris? What is this terrifying thing? And how is it related to the explosion? Before we reveal that, let's talk about what Polaris is. Polaris, also known as the North Star or Pole Star, is the brightest star in the Ursa Minor constellation, designated Alpha Ursae Minoris. With an apparent magnitude of around 1.98, it's easily visible to the naked eye at night. Its proximity to the North Celestial Pole, less than 1 degree away, establishes it as the current North Pole star, providing stability for navigation in the northern sky. Found a way to make a living in the ocean by gobbling up the carbon dioxide and giving off oxygen. They turn the sky blue. Being the closest Cepheid variable, Polaris plays a role in the cosmic distance ladder. According to the revised Hipparcos stellar parallax, Polaris is approximately 323 light-years away, equivalent to 133 parsecs. Compared to Polaris, the Gaia mission estimates a distance of about 448 light-years, equivalent to 137 parsecs. Despite appearing as a single point of light, Polaris is a triple star system consisting of the primary, a yellow supergiant named Polaris R, orbiting a smaller companion, Polaris AB. This pair also orbits a third component, Polaris B. William Herschel discovered the outer pair, designated AB, in August 1779, with a referring to the R or AB pair. Polaris R, an evolved yellow supergiant with a spectral type of F7 Eb and a mass of 5.4 solar masses, is the first classical Cepheid whose mass has been determined from its orbit. But that's not all. It has two smaller companions, which include Polaris B, a 1.39 solar mass F3 main sequence star orbiting at a distance of 2400 astronomical units, and Polaris AB, or P, a closely situated F6 main sequence star with a mass of 1.26 solar mass. Polaris B can be observed with a modest telescope, and William Herschel discovered it in August 1779 using one of the best telescopes of that era. In 1899, W. Campbell reported the variable radial velocity of Polaris A, suggesting it is a binary system. In 1927, G.H. Moore, recognizing Polaris A as a known Cepheid variable, demonstrated that the velocity changes along the line of sight were a result of a combination of the 4-day pulsation period, a much more extended orbital period, and a large eccentricity of approximately 0.6. Moore published preliminary orbital elements in 1929, indicating an orbital period of about 29.7 years with an eccentricity of 0.63. This period was later confirmed by proper motion studies performed by B.P. Gerasimovich in 1939. For her doctoral thesis in 1955, Roma utilized radial velocity data to determine an orbital period of 29.59 and 0.02 years and an 1963 to 1965. Initially attributed to secular redwood, a lower temperature evolution within the Cepheid instability strip. This change may result from interference between the primary and the first overtone pulsation modes. There is disagreement among authors regarding whether Polaris is a fundamental or first overtone pulsator, and if it is crossing the instability strip for the first time. While the temperature variation of Polaris during its pulsations is minimal, the extent of this variation is variable. and unpredictable. The erratic temperature changes and the amplitude of temperature fluctuations during each cycle, ranging from less than 50 K to at least 170 K, may be linked to the orbit with Polaris AB. According to Research and Science, Polaris is currently 2.5 times brighter than when observed by Ptolemy, transitioning from third to second magnitude. Astronomer Edward Ginnern deems this change remarkable, stating that if they are authentic, these changes are 100 times larger than those predicted by current theories of stellar evolution. But is Neil deGrasse Tyson spot on with his comment, "Hold on, because the best part is coming up"? Can Polaris explode? If so, how does this happen? A supernova is a brilliant and intense explosion originating from a star, which is Polaris. This phenomenon occurs in the final phases of evolution for a massive star, or when a white dwarf undergoes an uncontrolled nuclear fusion reaction. The initial celestial body, the progenitor, may contract into a neutron star or black hole, or be entirely disintegrated, creating a diffuse nebula. The maximum optical brightness of a supernova can rival that of an entire galaxy, gradually diminishing over several weeks or months. The latest supernova directly witnessed in the Milky Way was Kepler's supernova in 1604, following Tycho's space. In an attempt to finally lay this possibility to rest and put their minds at ease, scientists devised a way out. This novel solution involved instructing the axe to redirect telemetry data to the appropriate functioning data. They decided to go with this measure because it was considered low risk, and their bet turned out to be right at the end of the day. Although the solution was successfully implemented, they were faced with another challenge, which was the significant time delay in communication during this investigation. They were a bit worried by this outcome, but then it wasn't something worth losing their sleep over when we remember the vast distance that exists between the Voyager craft and the planet. The gap is so enormous that it is only fair to expect some delay in communication with a 14.5 billion miles distance between the craft and our dear planet. It takes a significant amount of time for radio signals to travel through from both locations. Here's how the communication between both parties plays out. Whenever the mission control team at NASA's Deep Space Network sends a command to the Voyager, it travels as a radio signal at the speed of light. The Deep Space Network (DSN) is an extensive network of massive radio antennas strategically positioned across the globe that makes it possible for NASA to maintain communication with spacecraft exploring the far reaches of our solar system and beyond. The primary objective of this network is to facilitate two-way communication between the Earth and deep space missions, alongside conducting radar and radio astronomy observations to widen our understanding of the universe. Whenever the Deep Space Network is transmitting data from the Voyager to the Earth, it often uses its channel 18 and usually makes use of frequencies 2.3 GHz or GHz. When we take a second look at this, we discover that when sending signals from the Earth to Voyager 1, a frequency of 2.1 GHz is used, and it occurs at the speed of light. As much as this traveling at the speed of light seems exciting, let's not forget the enormous distance separating both the probe and the Earth. Therefore, even at this supersonic speed, it takes the signal approximately 22 hours to reach the spacecraft. What this means is that after a command is transmitted, the missing control team has no choice but to wait for 22 hours before receiving any confirmation or response from the Voyager craft. This time delay explains why the mission team is very meticulous when it comes to the commands that they send to the Voyager 1. They are careful not to make any errors because it would increase their waiting time at the end of the day. They often spend hours reviewing commands and going over plans before they send them and initiate them to avoid issues and unnecessary delays. Time delays would prolong the period required to perform a diagnosis of anomalies, such as the one recently discovered by Voyager 1. Although the popular hypothesis is that the telemetry data sent to the Earth was likely caused by the axe receiving a faulty command from an onboard computer, researchers are far from satisfied. They believe that there is something still missing to complete this puzzle. Some researchers are still unsure of the exact cause of this anomaly, as there exist other possibilities such as cosmic radiation, extreme temperatures, and micrometeoroid impacts. The universe's environment can be a very harsh adversary, even for sophisticated spacecraft like the Voyager 1. Moreover, since the Voyager craft is waxing older, may have been a victim of the adverse and unforgiving space environment, all we can do for now is to keep our eyes glued on every one of these possibilities, because scientists may eventually find out which one of them is the guilty party. More so, let's cross our fingers for the next thrilling discovery that Voyager 1 will uncover as it keeps blazing through the deepest parts of the cosmos. Thanks for watching this video till the end. For more exciting space discoveries like this, click the next video on the screen.